Hello and welcome to Algebra 1, Lesson 26. In this video, we're going to learn about the product and power rules for exponents. So back in pre-algebra, we learned that whole number exponents, 1 or larger, were used as notation to display repeated multiplication of the same number. I want you to recall that the number being multiplied is known as the base, whereas the number of factors of the base is known as the exponent. So, for example, let's say we had something like 3 to the 5th power. 3, the bigger number, is known as the base. This, again, is the number that's going to be multiplied by itself. Then this little guy up here, this 5, is known as the exponent. This again tells us how many factors of the base that we have. So 3 to the 5th power is equal to 3 times 3 times 3 times 3 times 3. You have 1, 2, 3, 4, 5 factors of 3. As another kind of refresher, let's say I had 7 to the 4th power. Again, 7, the bigger number, is the base. And then 4, the little number up here, is the exponent. And again, this is telling me I have 4 factors of 7. So this is 7 times 7 times 7 times 7. 1, 2, 3, 4 factors of 7. Now we can also do this with variables. And in pre-algebra, we didn't talk about variables at all. But it would be the same thing if I said, okay, I have x to the 6th power. X would be the base, and 6 would be the exponent. So what would this be equal to? Well, I would just have 6 factors of x. So x times x times x times x times x times x. 1, 2, 3, 4, 5, 6 factors of x. So in a short time, we're going to start working with polynomials. And before we get to this topic, we have to have a complete understanding of how to work with exponents. It is very, very critical to your success with polynomials. So the first thing I'm going to teach you is called the product rule for exponents. So it's very, very simple, and it's very, very intuitive. We have a to the power of m times a to the power of n is equal to a to the power of m plus n. And I know some of you will have a glazed over look on your eyes right now, but essentially something you'd see in your textbook to kind of translate it into something you can understand. When we multiply two numbers or expressions in exponent form with the same base, so that's the key here, with the same base. Here I have a, and then I have the same a here. So what we do is we keep the base the same. So I don't change a at all, and then I just add the exponents. So you notice how the exponent here is m, and the exponent here is n, and we have m plus n right there. So even if that doesn't make sense right away, let's take a look at some examples and kind of let it set in a little bit. So we have 2 to the 4th power times 2 squared. So again, we're looking for the same base. So I have a base of 2, and I have a base of 2. So it's the same base. It's got to be the same number. If 1 is 2 and 1 is, let's say, 8, that's not going to work. The base has to be the same. So what I'm going to do is I'm going to keep that base the same. So I'm not going to change it. So it's going to stay as a 2. And then I'm just going to add the exponents. So I have an exponent here of 4, and I have an exponent here of 2. So I would do 4 plus 2, which is 6. So this is 2 to the 6th power. Now, where does this come from? Let's think about this for a second. If I have 2 to the 4th power, that's 2 times 2 times 2 times 2. It's 4 factors of 2. Now, if I multiply that by 2 squared, I'm essentially just multiplying it by another 2 factors. So 2 times 2. So this is 2 factors of 2. So to figure out how many total factors I have, I just add the number of factors I have here, which was 4, given to me by this exponent, to the number of factors I have here, which is 2, given to me by this exponent. So doesn't it make more sense just to go through and just keep the base the same, the number that's being multiplied by itself, and just add the exponents, right? Because that's going to tell me how many total factors of this base that I'm going to have in the end. This is a lot easier to do than writing all this out every time and saying, okay, this is 2 to the 6th power. And you can go through and evaluate this if you want. You don't have to. Usually at this stage of the game, they just want you to write 2 to the 6th power. But 2 to the 6th power is 2 times 2, which is 4, times another 2, which is 8, times 2 again, which is 16, times 2 once more, which is 32, and times 2 one more time, which is 64. And by the way, by the time you get out of Algebra 1, you're going to know up to 2 to the 8th power by heart because you're going to use it so often. All right, let's take a look at another one. We have 3 to the 5th power times 3 squared. So again, I'm looking to see that I have the same base. So this is the same as this. So there's my base, and there's my base. Here's my exponent. And here's my other exponent. Now, the rule tells me if I have the same base, which I do here, I'm going to keep the base the same. So just write a 3, and then I'm going to add the exponents. So I'm going to add 5 plus 2. So it would be 3 raised to the power of 5 plus 2, which is 3 to the 7th power. And again, one more time to get a complete understanding of this, if I had 3 to the 5th power, I'd have 3 times 3 times 3 times 3 times 3. Again, 5 factors of 3. Now, if I multiply by 3 squared, I'm just multiplying by 3 times 3. So this would be 2 factors. 2 factors of 3. So how many total factors of 3 do I have? Well, I have 7, right? I have 5 factors here, plus I have 2 factors here, which is exactly what I did up here. So I have 3 raised to the power of 5 plus 2, or 3 raised to the 7th power. And again, you can go through and evaluate that if you want, but that's not really what we're trying to do. We're just trying to kind of simplify it and put it in this form. Usually in your book, they're not going to say, hey, evaluate 3 to the 7th power. They're just going to say, what is 3 to the 5th power times 3 squared? Write that using an exponent, right? So that's what we've done. We have 3 to the 7th. All right, let's look at one with a variable. So we have x squared times x to the 4th power. So is there anything that's going to be different here? No. So I'm just going to do the same thing. I'm looking at the base. The base is the same. I have an x and I have an x. So when I do this multiplication, the base stays the same. I have x. And then I'm just going to add the exponents. I have a 2 here and a 4 here. So 2 plus 4 is 6. So this is x to the 6th power. All right, let's take a look at another one. We have z to the 8th power times z cubed. So can we extend this to multiplication where now we have 3 of these guys involved? Well, yes, we can. I know the original definition said a to the m times a to the n is equal to a to the power of m plus n, but it doesn't matter. I could go through and put z to the 4th times z to the 9th times z to the 12th. I can keep going and going and going. As long as the base is the same, okay, as long as the base is the same, there's really no limit. So base is the same, I keep it the same, and then I just add the exponents. So I have an exponent here of 8, then plus. Here I don't have a visible exponent. So what am I going to put? And this is very, very important. If you don't have a visible exponent, the exponent is 1. Because I have z to the 1st power there, or 1 single z. And it's very important that you put that because some students will skip that over and just put 0 there. Well, no, you have to account for that factor of z in the end result, right? So if you put a 0 there, you will be 1 short. Now this one is z cubed, so I'm going to put plus 3. So then I would have z to the power of 8 plus 1 is 9, then 9 plus 3 is 12. And again, if you wanted to write that out and see that you would be short if you left this one off, go ahead and write out 8 factors of z. You'd have z times 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 z. That's 8. 1, 2, 3, 4, 5, 6, 7, 8. Then you have 1 factor of z, so times z, and then times you have 3 factors of z, z times z times z. So as a total, you have 8 here, you have 1 here, and then you have 3 here. So that's 8 plus 1 plus 3, or 9 plus 3, which is 12. If I had not counted this one, if I had said, okay, well, there's no exponent there, so I'll leave it off, well, then you're not going to count this, and you're going to have 8 plus 3, which is 11. It's going to give you the wrong answer, right? So this is an understood exponent of 1. Make sure that if you come across that situation, you account for it. Okay, so the product rule for exponents, very, very simple, very, very easy to use. Just practice it and you'll memorize it very, very quickly. So the next thing we want to look at are some power rules. And kind of the first one would be the power to power rule. So that's where you have something like a to the power of m. So a is already raised to something, and then you raise that whole thing to another power. So a to the power of m is now raised to the power of n. And you can see this is equal to a raised to the power of m times n. So again, I don't like to give these kind of textbook definitions, but essentially you're just keeping the base the same. So this original base stays the same. So that's the same. And then you're just multiplying the exponents. So something like 3 squared raised to the 4th power. Again, keep this original base 3 the same. So keep this the same. And then just multiply the exponents. So I would have 2 times 4. So 3 raised to the power of 2 times 4, which is 3 raised to the power of 8. It's really, really that simple. You can kind of think about why this works. 3 squared is being raised to the 4th power. So that means I'm going to have 4 of these. So times 3 squared, times 3 squared, times 3 squared. So I already know from the product rule for exponents that we just learned, I would keep 3 the same, and I would have 2 plus 2, which is 4, plus 2, which is 6, plus 2, which is 8. So 3 to the 8th power. But another way that you could think about this is that this is going to happen 4 times. So if I have this many factors that's going to occur 4 times, I can just multiply. 2 times 4 would give me 8. That's kind of the shortcut. Because in the end, if I was to completely simplify this, I would end up with what? 2 factors of 3 times 2 factors of 3 times 2 factors of 3 times 2 factors of 3, or again, 3 to the 8th power. Let's take a look at 7 to the 5th power, and then this is raised to the 6th power. So again, I'm just going to keep the base 7 the same and multiply the exponents. So I'd multiply 5 times 6, and that's 30. So we get 7 to the 30th power. What about if we had a variable involved? Is anything going to be different? Well, no. If I have x to the 4th power, and then this is raised to the 3rd power, or cubed, I'm going to keep x the same. That's my base. And then I'm going to multiply. 4 times 3 is 12. So I would get x to the 12th power. What about z raised to the 9th power? And then this is raised to the 8th power. Again, z is going to stay the same. Multiply the exponents. 9 times 8 is 72. What about y to the 5th power? And then this whole thing is raised to the 3rd power. Again, keep the base the same. So y is going to stay the same. Multiply the exponents. 5 times 3 is 15. All right, so continuing with the power rules, the next thing we want to talk about is raising a product to a power. And this one can go back and forth. So sometimes you'll need to simplify. You'll start out in this format and you need to go to this format. Sometimes you start out in this format and you want to go to this format. You can go back and forth between the two. It doesn't really matter. So if I have this product here, which is a times b, so that product, and it's raised to the power of m, I can split it up and say this is equal to a to the power of m times b to the power of m. So in other words, if I have 2x and this is raised to the power of 2 or it's squared, I can break this up and say that I have 2 squared times x squared. Right? All I did was take this and make it an exponent on each one of those individually. Now I could further simplify this if I wanted to, because I know 2 squared is 4. So I could write this as 2 squared times x squared like that, or I could write it as 4x squared. And there's all kinds of manipulation that we're going to have to go through when we get to polynomials. It's just very important to know the rules so you know what's legal and what's not. So here we have an example of something that's presented a little differently. We have 4 squared times 3 squared. So to simplify this, if you get a problem, remember, I have the same exponent in each case. So what I can do is multiply the numbers or the bases together. So 4 times 3. And then it's raised to that exponent that they each have, which is 2. So I have 4 times 3. That's going to be squared. And we know 4 times 3 is 12, so we could write this as 12 squared. So again, just different ways to kind of simplify things. All right, what about 5xy? This is going to be raised to the 9th power. So we could simplify this and say we have 5 to the 9th power times x to the 9th power times y to the 9th power. So kind of separating this, each one is going to be raised to the 9th power. Or I could go the other way. If I got this on a test, I could write it this way, where I have 5xy raised to the 9th power because the exponent is the same in each case. What about 3zq raised to the 2nd power, or 3zq squared? Well, again, I can write this as 3 squared, z squared, q squared. What about negative 8x to the 4th power? Well, one of the interesting things here is you have this negative out in front. So you can write this as negative 8 to the 4th power times x to the 4th power. Now notice how I use parentheses around that negative. That's highly, highly, highly important when you're working with exponents, particularly when you have an exponent that's even. Remember that from pre-algebra. If I have something like negative 2 squared, it's not going to be equal to negative 2 inside of parentheses squared. These two are not going to be equal. This right here is basically saying I have the opposite of 2 squared. So it's kind of like negative 1 times 2 squared, which is negative 1 times 4, or negative 4. If I have negative 2 inside of parentheses squared, this is saying I have negative 2 times negative 2, which equals positive 4. So pay close attention to that, especially when we get into algebra, because you're going to be expected to know this, and most teachers are not really going to cover that again. They expect you to kind of remember that from pre-algebra. All right, so let's take a look at our last power rule. So we have a over b. So you can think of this as a fraction or division. Remember, those are the same. This is a divided by b, however you want to think about it. And this is raised to the power of m. Well, what we're saying is that this is equal to a, that numerator raised to the power of m, over b, that denominator raised to the power of m. And this, again, can go back and forth. Sometimes you'll need to write it this way. Sometimes you'll need to write it this way. But one thing to note is that b cannot be 0. And why is that the case? B is in the denominator. B is in the denominator. And we cannot divide by 0. Okay, it's undefined. All right, so we have 8 over 4, and this is raised to the 2nd power. So we could rewrite this as 8 squared, your numerator raised to that power, over 4 squared, your denominator raised to that power. And there's all kinds of different things you can do to simplify this. You know, if you wanted to, you could have canceled this with this to start and had 2. So this is 2 squared, or 4. But for the purposes of, kind of learning this, this is how we're going to simplify for right now. And you can kind of go through and prove this to yourself. We know 8 over 4 would be 2. 2 squared is 4. So that's what this is equal to. It's equal to 4. Over here, 8 squared is 64. 4 squared is what? That's 16. Well, if I divide 64 by 16, I do get 4. So it's the same either way. And of course it should be. This should be mathematically equal to this. And when we go through and do the simplification in this matter, we get 4. We go through and do it the kind of original way where we divide 8 by 4 to start, then raise it to the 2nd power, we also get 4. So again, it's the same either way. What about 5 halves raised to the 4th power? Well, again, I would just take 5, the number of the numerator, raise that to the 4th power, and put this over 2, the number of the denominator, raise that to the 4th power. What about x over y raised to the 7th power? Again, all I'm going to do is take x, that's what's in the numerator, and raise it to the 7th power. Put this over y, which is in the denominator, and raise that in the 7th power. Now, generally speaking, when we're working with variables, and we have a variable in our denominator, it's assumed that that variable in the denominator is not allowed to be 0 because that would be undefined. But you can specifically specify that y is not equal to 0. Okay, but again, if you don't put that, it's logical to assume that that variable cannot be 0. All right, what about z over 2q? And this is raised to the 14th power. So again, whatever's in the numerator, which is z, that's raised to the 14th power. And this is over. What's in the denominator? I have 2q. So the 2 would be raised to the power of 14. And so would the q. That would be raised to the power of 14 as well. You can kind of start out by thinking about it as, okay, this in the denominator, the 2q, is raised to the 14th power. We've already learned that if we have that, we can kind of separate the 2 and the q and raise each to the 14th power. So again, we end up writing this as 2 to the 14th power times q to the 14th power.